to do what it tells you to do. Yeah. Well, I tried webassign.com, webassign.net. It still forces you to create a Cengage account. Probably Cengage wants to buy WebAssign or already has bought it, I don't know. And on my side, I don't see, now I have to use this. Well, I can try again. Yep, and it will force me. But here, I don't see so far any difference. So they just have created a new database, so far at least, here. Well, yeah, at least 29 people succeeded to create the account and log in. So just keep trying. If it doesn't work so far, just try to fix it as soon as possible. Most important part is just the homework, of course. Well, so at least 29 students can answer the question on a WebAssign. So please do. This is a toy which helps to see the difference again between this type of a wave and that type of a wave. Here, wave travels horizontally, but each wave particle moves up and down, up and down. And here, the wave travels, well, in a vertical direction, and particles move in a vertical direction. And this is a model for this situation. So if we look like this, oops. Oops, it needs gravity, all right. And we have different names for these two different types of waves. And this one is longitudinal, number 2, yep. And again, it is helpful to play with applets. I do have a long spring, but there is no way in this room to attach it in a meaningful, convenient way. So this is a case when applet actually more helpful than actual physical demonstration. And if we look at any wave propagating in space, we can see that, let's take a pose, a snapshot. That's a photograph. A snapshot, a photograph, shows the profile of the wave at given instant, now, but everywhere. So we can draw the x-axis, and relative to that axis, right now, we can measure an instantaneous displacement from the equilibrium of every single wave particle. So this is the equilibrium, and this particle is displaced up by this much. This particle is at the equilibrium position. This particle displaced down below the equilibrium position. And for each particle, this displacement reaches maximum at some point. That maximum has a name, the amplitude. And each particle, for each particle, it takes exactly the same time to make one whole motion. That time we call the period. And again, if we use our imagination, we can imagine that we actually cut it out, this profile, and we move it to the right. So in a second, or in a fraction of a second, we would see something like this. So the wave propagates with a speed which basically describes how the profile of that wave travels in space. And speed is distance over time. So it takes exactly one period to travel in space, exactly one wavelength. The wavelength is the shortest distance between 2 points which move in phase with each other. So these 2 points move out of phase. We call it out of phase. These 2 points move in phase. And there's another one which moves in phase with those two, and another one. So the shortest distance between 2 points moving in phase, that's what we call the wavelength. This will be a half of a wavelength. This will be a quarter of a wavelength. The maximum displacement is the amplitude, and distance over time, wavelength divided by the period, that gives the wave speed, how fast the wave travels in space. And as we said, for each wave particle, it will take exactly one period to make one whole revolution and one whole oscillation. And one whole oscillation has 4 parts, 1, 2, 3, 4. So each wave particle travels distance which equals exactly 4 amplitudes in one period. And if we look just at one particle which moves in time at a certain location, to describe its instantaneous location relative to the equilibrium, we use another axis, y-axis, and this equation for the displacement of a particle as a function of time looks exactly like standard equation for a simple harmonic motion. So we can use the same relationships which we used in PY 105. This is a slide, and just to review the definitions. What is a period and how can we calculate it? If we calculate a time of 10 oscillations, the time of 10 oscillations divided by the number of oscillations, the period and frequency related, inversely proportional. Angular frequency tells us how many oscillations happens in 2 pi seconds. Nothing new. The only difference is that now what we called phase, this variable, also depends on location, on x. For different locations, the motion happening with the same period, with the same frequency, with the same amplitude, but slightly out of phase. So the goal is to write the wave equation, which is the kind of motion equation for the whole wave. And well, again, as we saw, if we understand how a single pulse travels, we understand how the whole wave travels. So if we look at the pulse traveling, it takes a certain time to travel a certain distance, but it travels at the same speed, which equals wavelength over period. And right now, this pulse has the same shape it had several seconds before when it was at the source, at the location of the source. So we can use this fact to derive very quickly the wave equation. So we can assume that the source oscillates like a cosine function or sine function or any function, doesn't really matter. So right here, this displacement from the equilibrium, and here means at its given value of x, and now means at this instant. So this displacement here and now is the same as it was at the origin this seconds before. And before means the subtracting, that's it. Now, how much time did it take? Well, distance equals speed times time, so time equals distance over speed. That's it. That's the motion equation for the wave. In particular, if we wiggle the end of a rope, for example, we'll call it a harmonic function, simple harmonic motion. So the wave equation will look like this. And all we need to do is just some manipulation to derive the equation, to rewrite the equation in a form every textbook writes it. First, this combination has a name. So we call it the wave number. In general, for a complicated wave which might travel in space, it could have been actually a vector, wave vector, but for one-dimensional wave, this is a wave number k. And it is related to, well, we can relate it to angular frequency and speed. And speed equals, again, where is it? On the previous slide, wavelength divided by period. So the wave vector is related to the wavelength directly. And, well, now we can answer lots of questions about waves. In my example, the pulse was traveling to the right. Well, we don't have to do it all the time. The wave might travel in the direction opposite to x-axis. So in that case, the wave number should change its sign. So here in this wave equation, the minus here came from the pulse traveling to the right. And here we see the profile of a wave traveling to the right at different instances. T equals 0. In a quarter of a period, it travels a quarter of a wavelength. In a half of a period, it travels to the right a half of a wavelength. In exactly one period, it travels to the right exactly one wavelength. But if we have a wave traveling to the left, all we have to do is just change minus to a plus. So a minus means wave travels in positive x direction, and for us, that's right. And a plus means the wave travels in negative x direction. That's it. And we're going to talk about this equation in the future, but this is an example of how we can calculate speed of a wave on a string. If we have a string, we can change the tension, and this is the force of tension in the string, and this mu is not a coefficient of friction. It's the linear density. This is the mass of 1 meter of the string. That's it. Now, so the summary, and to remember what does the minus or a plus say, and the question, what do you think about this situation? So in PY 105, we had a slide with many variations of motion equation for simple harmonic motion. And we know that it doesn't matter if we use a sine or a cosine. What we can't use is tangent or cotangent, but sine or cosine always represents simple harmonic motion. They, bless you, are interchangeable. Here we have a motion equation, a wave equation, and in a general form and a specific one. And all we need to do is just relate different parts of both equations. So each equation has exactly the same structure. Two equations, same structure. Certain number, function, another number, variable, another number, another variable. That's it. That's what we are looking for. We have a number and a function. We have another number and a variable. We have another number and another variable. So to make a transition from this general equation to that specific equation, what associations should be done? So what should we write for the amplitude? Exactly. We may need to convert it into meters just in case. 0.9, that's actually 9 millimeters. Yeah. Now, what should we write for angular frequency? Thank you. Again, just to review, people write it like this, and like this. With one exception, actually. It's, oops, huge. It's angular frequency, so that when they write it as a fraction, to make sure you you know that you have to use radians, they write it like this. And for k, we should write 1.2. Again, a meter to the negative first, 1.2, 1 over a meter, and that's it. We don't have any special name for wave number. Now, but the question is about period, and a period and angular frequency are related. This is how I remember this relationship, the easiest way for me, bless you, because it has no fraction bar. This product, period time frequency, angular frequency, is always equal to 2 pi, always. Well, in this particular situation, it will be equal period will be equal to 2 pi over 5, which is I got about 1.3, right? Seconds. 1.3 is less than 5, that's it. Any questions? So again, this part is not new. Yeah, simple harmonic motion. Now we're adding one more equation and answering many questions. Well, basically, it says, it just used white ink, but it says find everything. So we can use this equation for calculating the speed. We're assuming it's a relatively long string, so the wave travels in space and time, and that's supposed to be equal to the force of tension divided by, well, that's supposed to be m over L, and actually we don't know the tension, so probably we'll have to find it. Tension, and that's supposed to be, well, we have to convert grams into kilograms and divide by length, and that's it. That's all we can do for now. 0.012. So I guess we will have to solve it. So for the tension, that will be equal to speed squared times 0.012. But the speed is supposed to be equal to the wavelength divided by the period. And we know the period, it is what 1.3, right? 1.3 seconds. So how do we get the wavelength? Well, all right. This is the case when we need it, but we don't know it. So what do we have to do? We have to find it. So we search for additional connections, and we have that additional connection, which we didn't have for a simple harmonic motion, but we do have for a wave. The wave number is related to, or you can remember again, this relationship like this. The product, k and lambda, is constant. So we can use this for calculating lambda, 2 pi over 1.2. Calculator just died. Oh, now it's on. Something is really, really strange happening here, like a Bermuda Triangle. What do you do? 2 pi. All right. About 5.2 meters. So now we can use this number back in this equation for calculating speed. About 4 meters per second. And now we can calculate what was tension in that string. 4 squared times 0.12. So what? About 0.2 newtons. So I find this type of problems very straightforward. And of course, we can calculate the displacement from equilibrium at any location, at any instant. For example, y at, I don't know, 2 meters from the origin at t equals 2 seconds. So, and let's use millimeters, 9 millimeters, oh, like a bullet, sine. So 5 times 2 minus 1.2 times 2, so 9 millimeters times the sine of, well, 2 and 2 common factor, 5 minus 1.2, 3.8, 3.8 times 2, 7.6. So now you need to take a calculator and calculate it and tell me your number. Now, 9 times sine of 7.6. 1.2. Now, someone should tell me if this is a correct number or wrong number, and so far I don't know, but I know it might be wrong. It depends on how you use your calculator. And how did you use a calculator? 7.6, what was that in your calculator? Your calculator was set to degrees, but 7.6, not degrees. And people forget that and make mistake. So what do? You have to switch your calculator from degrees to radians. Did you? So what's your new number? So this number is radians. That's it. Of course, you could have done it differently. 7.6 radians, we can convert into degrees and just use our calculator in degrees. Pi radians equals 180 degrees. That's a conversion factor. Any questions, please? So these are slides, probably more accurate calculation or less accurate calculation. Yeah. Now, question number 4. You have 2. Well, 2 what? It depends. If we take in math class, we call them graphs. But in physics class, only one technically is a graph, but another is a snapshot of a wave, a photograph. A graph is an abstract representation of something happening. A photograph, well, it's an actual object. We can print it out. We can look at it. And what do you think? Which, say, line, the blue one or the red one, represents a photograph? Bless you. But you can't enter that into WebAssign. What do you think? You don't have access to WebAssign, should say. And why? That's exactly right. A photograph is a snapshot. Thank you. Bless you. For confirmation of what I said. It's a snapshot. So a snapshot shows something happening in space at a given instant. So we should imagine that we have a ruler, which we call x-axis, and maybe a second ruler. Yeah? And someone waves one end of a rope, and we take a photograph, and it's spaced from origin to wherever. This is a graph which represents oscillation at a given location, we don't know which location, maybe at the origin, maybe somewhere else, but at different instances. Oops. So, and we can extract a lot of information from this photograph. For example, the amplitude, the wavelength. This is the amplitude. Sometimes it's easier to see the whole span and divide by 2. So the amplitude will be equal to 8 minus -8 divided by 2, which is 8 millimeters. What's the wavelength? Well, we need to apply a definition. It should be distance, the shortest distance between 2 points oscillating in phase. In phase means at the same time they have the same displacement from equilibrium. So this is supposed to be the wavelength. The wavelength 60 minus 20, 40 centimeters. We should keep an eye on units. And where else can we find? Well, it travels to the right, and the speed equals 20 centimeters per second, or 0.2 meter per second. And that's it. We can calculate the wave vector 2 pi over lambda. Now, speed. There are two, I would say, equally convenient relationships between speed, wavelength, and what? Well, it depends. We can use an expression like this, but very often, and we will see soon, when the second equation is more convenient. Speed is equal to the product, well, no fraction bar, so it is multiplying wavelength and frequency. But in this situation, we can use it, for example, to calculate the period. .4, 0.2, 2 seconds. So the frequency will be 1 over period, 1 over 2 Hz. The wave vector 2 pi over 0.4. Pi over 2 over 40. No, what do I do? It's 20 over 4. Eraser. 20 divided by 4 is 5, so 5 pi. And I want to keep the number pi. And angular frequency, 2 pi regular frequency, just a pi. Now we can combine everything, and let's see. This is a snapshot at t equals 0. All right. And this is a cosine. So at t equals 0, the displacement from the equilibrium equals a cosine well, cosine is an even function, so we can write plus or minus k times x. But for a wave traveling to the right, it should be a minus, as we know. So at any instant, that should be a cosine omega times time minus kx. and we can actually write it in numbers. The amplitude is, well, 8 millimeters, right? Cosine pi. We have two running variables, time and location x coordinate. And even we didn't ask, oh no, we did. Yeah, we can calculate the maximum speed, Vmax, the maximum speed of oscillations. That's supposed to be amplitude times angular frequency. And now I guess we need meters, 0.08 times pi. That's going to be meters per second. So again, just straightforward application of all set of equations we use, plus some information came from looking at that snapshot. Amplitude and wavelength. If instead of a snapshot, we would have, probably we do, yeah, no, okay, let's go back for a second. If instead of a snapshot, we have a graph, what can we extract? Well, still amplitude, but if we look at this, instead of the wavelength, that will be a period. From this to this oscillation, it passed exactly one period. So for this particular situation, for this particular example, one period will be equal to 40 milliseconds, whatever it is. We just need to read it. Any questions? All right, now, what's going to happen if we're adding waves? So we know everything about one wave. Now we got to start adding. Well, of course, we're not going to go, at least for now, to a large number of waves, only two. And again, you know what? Who's brave enough? Who's brave enough to help me out? Go ahead. All you need to just hold it, and hold it tight, because if you release it, it might kill me. So just look closely. If I make one pulse, so I'm the source, it travels actually very fast, and when it reaches the hand of this brave gentleman, it travels back. It's a reflection. Wave reflects, like echo. Echo! See? Well, here. So, and if I start waving, what do I have? Two waves now, in the same medium, on the same rope. One wave travels away from me, then it reflects, and second wave, reflected wave, travels back. And in the end, what we may have, a variety of situations, maybe nothing interesting, but maybe something special like this, or like this. And if you look at this wave, for example, which is a combination of two traveling waves, but this wave doesn't move. Thank you very much. That's what we call a standing wave. And that's our immediate goal, to figure out how to describe standing waves. Standing waves actually have many applications. One wrong move and your back brings you back. So, making sounds. By spinning it with different speed, I can generate sounds with different frequencies, but specific only specific frequencies survive. I can try to generate others, but we can hear clearly only certain ones. This musical device has a name, a bluegill, and you will be playing with similar devices tomorrow and day after tomorrow. And I encourage you, if you have fun, if you want to have fun, bring some musical instrument and musical instruments based on this theory. If you want to tune the guitar, for example, all you have to do, you have to change the tension in the string. And when you change the tension, it changes the speed. And when you change the speed, you change frequency. This guitar has been beaten many, many times, so it has glue, it has a screw, but still sounds not bad. Now it's, yeah, neck is also kind of beaten. We don't know why some combination of sounds good to us. It makes like us, you know, feel happiness or sadness. And some, you know, excite some nasty feelings. We don't know, but we use it heavily. Now, different type of instruments. That's an instrument, a whistle. But there's only one type of sound you can generate in this whistle, well, easily at least. This one. And you can, well, it's not a bluegill, it's harder to generate a wave with different frequency. Pipes, how do we use them? Well, it's a pipe which makes sound, right? Well, actually better, this is actually an actual organ pipe. You can change the tone by changing how much air column is inside it, by moving the piston. So we can calculate the exact frequency generated inside this pipe eventually, if we learn all this theory. What else do I have? All right. It doesn't really work reliably as all other instruments, but I'm going to give it a try. It's a model of, well, in the winter, if you have a house, this is a pipe, and when I hit the air, as we know, hot air travels up, and it travels up, and it generates that sound. But again, you don't hear several different sounds. You hear only one. So every standing wave has the, we call it modes or harmonics, but there's always the lowest one which can be generated, and then the next higher and the next higher. Human ear normally can hear only the lowest or maybe the next one. Some people can hear 3 modes, but it's really, really, well, you have to be a musician probably, or a director. So this is what we're going to talk about, and mathematically it's about vectors and vector addition. So what happening if we have one pulse traveling, let's say, to the left, and on a same rope, or in the same medium, another traveling to the right. This is what we call the displacement number 1. This is what we call the displacement number 2. When we should observe what we call superposition, which basically just addition. Well, when they start overlapping. So this would have been a pulse number 1, and this is slightly wider. Right? Okay. This would have been, let's say, a pulse number 2 at this particular instant, but the resulting shape will be something different. And for example, right here, right now, the net displacement should be equal to the sum of 2 displacements. So it should be something like, well, like this. Y equals Y1 plus Y2. That's it. And that happens everywhere. Yeah. So if we have a wave, all we have to do is just add 2 functions. And if we have simple harmonic waves, we have to add a sine and a sine, or a sine and a cosine, or a cosine and cosine. And we don't have to do that. We can. We don't have to. Because, well, first of all, there is an easier approach to figure out what kind of a standing wave will be generated. We'll talk about it in a minute. We will talk about 2 specific cases only. Case number 1. When those waves have very, very close frequencies, different, but close. In that case, what's going to happen? Well, that's what's going to happen. So this is a tuning fork and another tuning fork. Well, first of all, they both generate the same sound, pure tone, A1, 440 hertz, because I can read it, same tone. Actually, that's what resonance is. Yeah. I hit this one, but it excites. But it excites the second tuning fork, but that only happens when they have exactly the same frequencies. It's not going to resonate anymore, nothing. They must have exactly the same frequencies. But if they have different, slightly different frequencies, you can hear that the sound actually kind of changes in loudness. Yeah, well, I do have slightly better setup in a minute. I can hear it because I'm close, but when the wave travels toward you, the intensity decreases. So, well, it's a nice toy, but nowadays we have much more powerful devices. We call them speakers. You hear? This one generates tone with 1000 hertz, and this is 1001.2. The difference is 1.2 hertz. And the more difference is, the faster loudness changes. And that's what we call, actually, beats. And it has practical applications because we can measure beat frequency, and then if we know the beat frequency, we can measure the actual frequency of a source if we need it. Even some of versions of police radars use this, but not sound, of course, radio waves. Beats. And a second situation, when frequencies are exactly the same, that's where we're getting standing waves. And there are two situations when we have one source and then another wave is reflected. And a second situation when we have two sources with identical frequencies, like two speakers. There is some difference between these situations. Beats. Well, we saw, well, we didn't actually. Beats. What's happening here? Let's say fundamental. Oops. What's happening here? Okay, this is an illustration of a superposition. One wave travels to the right, second wave travels to the left, and at the bottom we observe what would be happening if they would be traveling in the same medium. So, and eventually we observe a standing wave. In this standing wave, you can see that both ends move, this and that. And that's not always the case. For example, if we have a string attached to two doorknobs, those ends will not move, but we still will be able to generate a standing wave. All right. So what's happening here? That's going to be, again, an example of a superposition. One wave travels, second wave travels, and we can see the resultant. The resultant, the pink one, is always an addition of two displacements here and now. Now, these are supposed to be beats, I suppose. Yeah. So let's make small. So here we have two waves, and you actually don't see practically the difference in the wavelength. So, but we can see when we add them up together, the resulting wave has changing amplitude. The amplitude reaches maximum, and that's what we heard, you know, the loud part of the beats, and then the amplitude goes down. So that would have been something like, let me start from maximum. Etc., etc. Beats. And here, so there is a slide with all links, but by some reason today in the morning, Firefox didn't work with any of these applets, but old-fashioned Internet Explorer actually did. All right, again, an example of wave superposition. Two traveling wave produce one standing wave. Let's see. So a wave travels to the right. get reflected eventually, travels to the left, superposition. Probably, okay, let's see. Probably we're going to have a tube. So you see, it says wave in a tube. So we should generate a standing wave. It's not a standing wave yet. So there is a process. It takes, well, normally, of course, fraction of a second to generate a standing wave of a given frequency. And this is an example when one end of a wave doesn't move at all, but second wave moves, which means this is a tube which has one end closed and one end open. All right, so beats. If we calculate the difference between the frequency of the first wave and the frequency of the second wave, that's what we actually get for the frequency of the beats. And 2 pi over frequency, angular frequency gives the period. So we have an example. So please just enter your choice. So we have a tuning fork number 1, and we have a tuning fork number 2. We know one tuning fork generates sound with frequency equal to 400 hertz, and we hear the beats. Beat frequency is 5 hertz, which means the loudness changes 5 times per second. And this problem is to remind us what this means mathematically. Absolute value, magnitude. So the equation says 5 is supposed to be equal to the difference between 400 and something else. But again, this is not this. What's the difference? The magnitude of a positive number is positive number, but the magnitude of a negative number is also negative number. So technically what we have here is 2 possibilities. That's one. That's another one. And if we have 2 possibilities, we have 2 possible answers. That's it. Any questions? Now, standing waves. This is an example which says, do not read this slide, so close your eyes, please. What could have been done? Theoretically, we could have been doing this mathematics. You can Google how to add if you don't remember. I don't remember, but I can figure it out. And you can figure it out. If you need to add, like in this example, 2 signs, there is an equation which tells us the result, and the result would look like this. And this wave travels to the right. You can see a minus. This wave travels to the left. We call these waves coherent. And only coherent waves can produce a standing wave. They have exactly the same amplitude, exactly the same wavelength, exactly the same period, exactly the same speed, just opposite directions. And in this situation, if we add them up, the structure of the wave is different. There is no minus or plus. We have a part which is related to time only, and we have a part which is related to amplitude, to the position only. So this actually looks exactly like standard, simple harmonic motion. And it is a standard simple harmonic motion. But the amplitude of that motion depends on the location. In a standing wave, as we saw, some points move with the largest span possible, and some points don't move at all. So so these are pictures just from those applets. An example of a standing wave on a string. The wave number 1, the wave number 2 represent two coherent waves traveling toward each other. And the pink one represents the actual profile which we would see if we took a picture of that string. And as you saw, there is an instant when the whole string is horizontal. But then different parts of a string move, and we can see something like this. And from this, for example, to this, we should wait a quarter of a period. This is one period, 0, quarter, half, 3/4, and back to initial. So some points don't move at all, which, well, this, for example, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, this point, this point, this point, it's the same point in space. And we don't see any motion at that point. We call it a node. A node. A point inside a wave which does not move. But some points move up and down. One, 2, 3, 4, 5, 6. 1, 2, 3, 4. Wrong one. It's a counting problem. So, 1, 2, 3, 4, 6. Here. Why it doesn't move? Because you see these displacements. Oh, this is also wrong location. These displacements always cancel each other out completely. This has to be here. So at every instant, at this particular location, two displacements always cancel each other. I just erased you. All right. That's why there is no motion. But it's only here or here, another node. Again, two displacements always out of phase, always cancel each other out. But here or here, they always in the same direction. That's why we get the maximum of the amplitude. And that's what we call the antinode or antinode. People call it differently. So that terminology, people also use like for this called minimum or trough, maximum or hill, crest, different names. And every standing wave always has exactly the same structure. Nodes, antinodes, nodes, antinodes. And for example, shortest distance from an antinode to node, this is always a quarter of a wavelength. This will be a half. This will be the exact wavelength. So it's handy, it's helpful to know these facts. Antinode, antinode, a node, a quarter of a wavelength. please. Tell me what you think. Short memory test. These equations have very different structure, and the structure of an equation tells us what does it describe. And for us, only two things might happen. A wave might be traveling in space from a source away from it, or a wave might represent a superposition of two waves, stable superposition of two waves, a toy which you also could buy where? eBay. That's what where this came from. So this is not a stable profile. It's not a standing wave. I will have to make some adjustments. I can make it move faster or change the tension. And now this is a standing wave. So to generate a standing wave, we must fit together several parameters: tension, speed, distance. I can break it again and try to generate a different type of standing wave, different type of standing wave. For example, I can try to make 3. Okay. So I've made a different adjustment, and now I can see 3 empty nodes. So I could play all day with this. And the structure of an equation tells us this is a standing wave, so it should have a stable profile. This is not a standing wave. And that was question number 6. 4 is the most popular. 4 is the correct. When we have a minus or a plus, when time and position combined inside one function, that describes wave traveling in space, in this situation, to the right. But if we have 2 different functions, one is responsible only for what's happening in time, another where it's happening, that is always a standing wave. And again, sine or cosine doesn't really matter. Could be sine and sine or any variation. So again, that's what could have been done. And traveling and traveling makes it standing. This is what you can try if you like algebra. These are the equations which can be used to calculate a profile of a standing wave, if you know what type traveling waves have. And for any standing wave, we only have, well, in general, 3 situations. Case number 1, one end of a wave doesn't move, another moves. Case number 2, both ends move or both ends fixed. And our goal now is to derive an equation for the modes, harmonics, which could be generated in those devices. This is a pipe or a tube with both ends open. So the question, what do you think? What type of a wave should be generated in a pipe with both ends open, or a tube like this one? Higher. Oh, this is a musical instrument, yeah. Or signaling instrument. Yeah, you're signaling. What did you say? What type of a wave should be generated if both ends are open? What should we observe for a stable standing wave? That's important. Yeah. And it's related to air. Air motion is happening, and the air molecules move at each end and inside, and technically those molecules move in this direction parallel to the tube. And for a stable standing wave, loud standing wave, they should travel here, well, oscillate here and here with the maximum amplitude. And that location has a name, an antinode. That's it. And for the antinode, the shortest wave, for two antinodes, the shortest wave which fits the pipe should have antinodes moving out of phase. And this is a pictorial representation. As we said, actual molecules move horizontally, well, like this, like this. But it's really not convenient just drawing the longitudinal wave. So we always draw some kind of a piece of a rope, which, because it's easy to imagine, which represents the situation happening inside a tube or a pipe. So if we have a tube or a pipe and both ends are open, we should be able to fit a certain amount of, well, lambda in such a way so both ends would observe an antinode. So this is how any generic or general standing wave looks like. Yeah? Photograph. An antinode, another antinode, another antinode, another antinode. So the smallest amount which satisfies this condition, the smallest amount, the shortest part of a wave, which has two antinodes, is equal to a half of a wavelength. So we can imagine I cut it out, stretch it a little, and fit it in this tube. And this picture represents the longest possible wavelength, the lowest tone. We call it the fundamental, or the first mode, or the first harmonic. And of course, if this is a quarter of a wavelength, this is a quarter of a wavelength, and this is the length of that tube. For the first mode, the relationship between the length and the wavelength is this. So we can solve it. Well, this is the first one, or the fundamental one. We can solve it for the wavelength. What would be the next possible mode? Well, the next possible mode for the same tube open on both ends should have, again, two empty nodes, but it also might have an additional empty node inside. So this picture represents the next possible mode, the second mode. And the relationship between the length of the tube and the wavelength number 2 is this. But it is actually more convenient to write it in terms of halves of a wavelength. Because the next mode, which can be generated in the same tube, the third mode, should have again an antinode here, an opposite antinode here, and two antinodes. We're adding antinodes every time. So again, now I can imagine I take this, but now I kind of squeeze it to fit it in the tube. Antinodes, antinodes, a node, a node, an antinode, a node, an antinode, a node, an antinode, a node. That's the general structure of any standing wave. A node, antinode, a node, antinode. That's always a quarter of a wavelength. That's always a half of a wavelength. We're just adding halves. So that's going to be down, up, down again, yeah, something like this. And that should fit 3/2 of a wavelength. That's for the third possible mode. And of course, you can use your pattern recognition machine, which is a brain, and see the pattern. For the first mode, we have to fit 1/2 of a wavelength, for the second 2, for the third 3, for the fourth 4, for the nth n. So the general equation for any mode number n, which we can generate in a pipe or a tube with both ends open, is this. We don't have to do mathematics if we can do physics. We could have added 2 sines or cosines and then analyze, but we could just do physics. And of course, we can solve it for the wavelength number, and the wavelength number n will be equal to 2 times length of a pipe divided by the number. But normally people don't calculate wavelength, they calculate frequency. Speed equals wavelength number n times frequency number n. Do I need a subscript for the speed? No, it's the same medium, same air, same temperature, same pressure. So for all these modes, the speed is the same. And if I want to solve this equation for the frequency, frequency will be equal to speed divided by the wavelength, the nth frequency. Yeah. So n, speed, and this number n runs from 1, well, technically to infinity. But every next mode will be less energetic. So n means the lowest fundamental frequency. And we can see that the relationship, so the fundamental frequency is equal to speed over 2 times length. The relationship between the nth mode and the fundamental is very simple. Any questions? Now, I'm going to jump ahead and I'm going to tell you a secret. If we have a string with both ends fixed, so clamped, that's a clamp, that's not a propeller. You tied it. So if you have a string with both ends fixed, you can use exactly the same set of equations. There is no difference at all. So again, a standard generic shape of a wave looks like this. If both ends fixed, we can't have antinodes. We must have two nodes, and the shortest distance between two nodes is a half of a wavelength. So if the length of the string is equal to L, we start again counting from a half of a wavelength, and then we're adding another half and another half. So the fundamental still equals this, but the speed now, of course, is not the speed of the sound in air. That speed for waves on a string, but the equation which relates modes and length is exactly the same. So it doesn't really matter if both ends are open or both ends are fixed. As long as both ends are the same, this is the equations we can use. Now, so these are pictures and equations. No, I'm not going to do that. I want to skip it for now. And this is not also a question. Let's just think it through. Now we have a situation when one end is fixed, but another end is free. And of course now, at the free end, we should have an antinode, but at the fixed end, we should have a node, no motion at all. Air molecule would kind of stick to the wall, to the piston, or if we had a string or something elastic rod, we could wobble. Yeah, it would be just held. And in this situation, there is a difference in how we count modes. So of course we can do mathematics. Sorry. But we just have to draw again several pictorial representations. So again, this is a general shape of a standing wave. And we need to start from the shortest part of this wave, which has one node and one antinode. So this crest, bump, hill represents the location of antinode, no motion at all, the node. And this is actually a quarter of a wavelength. So the smallest part of a wave, which can be over, again, stable, standing wave, which can be fit, has a quarter of a wavelength fit in the pipe. That's L. So for the fundamental, for the mode, the relationship is 1 times a quarter of a wavelength. Now, the tricky part is we cannot move to the next antinode. We can't. It's forbidden. Because we must have a node again. So the next possible point is this. And this is not a half of a wavelength. What part of a wavelength is this? 1/4, second, third. 3. quarters of a wavelength could be fit in the same. So we shrink the wavelength. The wavelength decreases, which means frequency increases. So that's supposed to be a node, and a second node, an antinode in between, and an antinode here. So something like this could represent the shape of that part of a wave. And now the relationship is different. So 3 quarters. And now we got a problem, because different people, different textbooks count them differently. Some people say this is the second mode, and I wrote it too. But in that case, if I look at the numbering the modes, and this number, which I use to calculate the wavelength, they don't match. So what do I do? And many others, they say it's not the second mode, it's the next mode, which is the third one, and the second doesn't exist. That's what people say. Yes?
Why do you need to include that second mode? First overtone. You have to skip the node, right, to go to 3 quarters?
Because if, well, all right. Because if you didn't skip it, you would have an antinode on both ends, and that's forbidden. This end must have a node.
Because it's fixed on one end?
Yep.
Okay.
So this is a specific feature of a situation when one end is fixed. It can't move. So that's why we have to skip that antinode. And of course, now we know what to do. We say, there is no mode number 4, but there is the mode number 5, which generated if we fit exactly 5 quarters of a wavelength. So then next relationship should be written like this. And of course, now we can see how we count those modes. We use numbers 1, 3, 5. But we skip numbers 2, 4, 6, so we don't use any even number. We have to use only odd numbers. And we don't count halves, we count quarters. So the equation, the general equation, I'm going to add one more slide. All right, last equation. Come on, work. So the pipe, one end open, one end closed, or something flexible, a string is one end open, one end closed. So the length of the pipe always should be equal to this. But this number must be odd. 1, 3, 5, 7, etc., etc. And of course, speed again equals frequency number n times wavelength number n, and we can calculate the frequency if we want to. The frequency number n equals speed divided by the wavelength number n. All right, we are done. Thank you very much. And please sign out before you leave.